Thanks, Christian. Right. Say, can everyone hear me? Right. Say, if you can't see me, right, and can everyone see my slides? Let's just make this sure first.
Yes to both.
Yeah. We
All
see.
right. Okay. Yeah. All right. Okay. Yeah. Thank you. So, good morning from Vienna, or good afternoon in India. Joachim Hermission, theoretical population genetics from Vienna. I'm going to talk to you about oligogenic adaptation. Let's see. All right. So the work that I'm going to present is joint work with Ilse Höllinger and Ben Wölfe, and goes back a few years to the thesis by Ilse Höllinger, a paper from 2019, where we first introduced the method, using it on a sort of a toy model first. And then we had a larger publication last year in genetics, which will make the bulk also of my talk today. And then also with Ben Wölfe's PhD thesis, there were, all the additional results about models with unequal locus effects, and all this is unpublished or only published as a thesis by Ben Wölfe, and we are still on it, but I'm going to present you some results from that also. All right, so I think as scientists, our ultimate goal probably always is to provide narratives about natural processes. So an answer in the end should not just be like a mathematical formula, but should be like some picture or narrative that everybody can understand with some intuition, right, about things go about in nature. But now, if we ask what is the state of affairs with adaptation, or how does adaptation come about, this picture or narrative still very much depends on whom you ask. Of course, all the foundations have long been laid by Darwin and Wallace, but beyond that, it's still, we have these two different ideas coming, rather from the molecular PopGen side or from quantitative genetics. And, you've seen this before, of course, in Neda's talk. On the one hand, from molecular PopGen, so the image that people think about is consecutive sweeps. Whereas on the other hand, in quantitative genetics, so the idea is we have these very tiny shifts at a very, very large number of loci. And obviously, everybody also knows that both of these views are at least sometimes true, right? But then, of course, so the question remains, can we really demarcate the conditions under which we either get one or the other scenario? And also, what do we have in between? So this does not only, of course, have differences, say, to the trajectories of selected alleles themselves, but also to the footprints around them, where we have these very strong footprints for sweeps, but very tiny things that are hard to detect for small shifts on the quantitative genetic side. So what happens in between? And all right, of course, to answer that, what we need is a model. And the model I'm going to talk about is not just any model, but it is the arguably most important model of quantitative genetics. It's an additive trait. So under stabilizing selection, so you've all seen this before, of course, here Gaussian fitness function, and here we have an additive trait, just here in this figure. So some phenotype distribution here, like say a fitness landscape here, Gaussian fitness landscape around an initial optimum here. And then we will assume that at some certain point in time with an environmental change, this optimum shifts to a new position. And subsequently, so the population will react, and the mean trait will approach here this new optimum. And while doing so, we are interested in the joint distribution of mutant frequencies pi. So we are interested in how this change in the phenotype is accomplished on the level of the genetics. So which locus contributes how much to this progress here. And this is what we call the architecture of poly or oligogenic adaptation. So how is a recent adaptive phenotype the one produced by underlying genotype? That will be the question. All right, so how can we approach this mathematically? So if we look at these both sides, sweeps and shifts, we see that very different model approaches are used here and there. Obviously, on the side of sweeps, so we can make use of the usual 1 or 2 locus models of population genetics. And this has been done a lot, starting with Maynard Smith and Hay sweep paper in 1974. And there is loads of theory around. On the other hand, on the side of small shifts, for a long time, people have not been concerned so much about the genetic changes, but rather stick to the phenotype and then argued that, the details on the genetic level are largely irrelevant. But of course, recently with GWAS, now that we do have all these genetic information, this has changed. And there is also a lot of theory like connecting phenotypic changes to the underlying genetics. And in this case, right, because, small shifts are small shifts, right? The obvious way to approach this is perturbation theory. So you have some standing genetic variation to start with. And often, so the main, task first of all is to characterize the standing genetic variation maybe in mutation selection drift balance. And once this is done, then directional selection sets in, and so this works as a perturbation, right? Say all the allele frequencies will shift proportional to the contribution of each locus to the additive genetic variant. So this is basically it, if it's only like a little bit. And these additive genetic variants locally can be assumed constant. So a recent paper that did this in a very nice way is the Hayward and Seller paper that you probably also all know. Now, but what can be done in between, right? And it's the in-between where I think the largest problems are really, and these problems arise because we do not have small shifts here, but we do have or need to account for large allele frequency changes and at many loci in parallel. So we can neither use this perturbation theory here on that side, or also we cannot do with 1 or 2 locus models, right? And the problem largely comes about because, stochasticity definitely matters, but also interactions in the sense of fitness epistasis cannot be ignored, right? And this is not a nice, combination of problems, and so one needs to think about what to do in this situation. All right, so here's a schematic of what can be done, and ideas, of course, say are in the end also relatively obvious, like how this could maybe be approached. All right, so what do we see here? Here we see time on the x-axis, and so you see here a cartoon version of evolutionary trajectories at two loci, right? Say the orange one and the blue one that increase in frequency from around 0 here, or occur as a new mutation here, and then increase in frequency to some levels here, at the end. And the total time here is dissected into different phases. So we have first stabilizing selection here. So this is supposed to be in mutation selection drift balance, our trait, right? And then we have the evolutionary change. At that point, the trait just moves to a new optimum. And the first thing now is the rapid phenotypic adaptation phase that relatively quickly will bring the trait mean close to the new optimum. And in the end, then we have this phase of slow changes when the allele frequencies then equilibrate around the new optimum. Also, these two phases you remember maybe from Neda's talk here. All right, so in this talk, I will entirely be concerned with this rapid phenotypic adaptation phase, right? Where we sample somewhere here, right? Before these changes really get too slow. The idea is that during this rapid phase, selection is strong enough, or selection on the level of the trait is strong enough that we can hope that this is really the major evolutionary force that drives things forward, plus drift, of course. Drift can never be ignored, right? Whereas, like in this phase of slow changes here, right, everything becomes very, very vulnerable to pleiotropy, to other effects, to whatever, right? So that, say it's maybe interesting, first of all, to focus on this rapid adaptation phase where things may be a bit more stable if we deviate from model assumptions. Okay, so, now concerning the maths of oligogenic adaptation, what I said here, right, is, say we dissect things further. We say we have a phase where allele frequencies are initially very low. And this can be either even before the environmental change, so allele frequencies this here in the standing genetic variation here, or alleles that come in as new mutation after the environmental change also obviously start at low frequency. That's called the establishment phase. And during this phase, definitely stochastic forces are very relevant. It's largely governed by mutation and drift here. And the whole thing can be described as a branching process. Of course, also selection, but what's not important here in this establishment phase are interactions among segregating mutations. And this is what makes our life here simpler, and why we can go to a branching process, as I will explain further, because we can largely ignore interactions here. Now then, a little later, when, say these allele frequencies have grown, then, epistatic interactions do become important, can no longer be ignored. However, now, so since these allele frequencies are larger, so we can ignore further action of genetic drift. We are in this competition phase, right? And we can use deterministic theory to describe things from here on. And then, of course, the problem remains, how do we combine this branching process phase to this competition phase here? And I will talk about this, of course, also. And then at some point here, we sample, right? Before, as I said, we progress to this slow change phase where we have equilibration around the new optimum. All right, so this is sort of the program, so for the first part of my talk. And since this, I do have a little longer time today, I will not skip all the methods, right? So this should not be seen as a threat. So I won't throw around formulas too much, but I will try as good as it gets to give you an intuition, how we approach this in these different phases, in the establishment phase and then in the competition phase, and what are the ingredients that are needed to get our results. Right, so let us start this with the establishment phase. So we do model mutation and drift during establishment as they create stochastic differences among these loci. Right? So all these stochastic differences that in the end also make up large parts of the result, right, among these loci, indeed do come from this establishment phase, why all these alleles are rare, either before the environmental change or after the environmental change. Okay, so what is a Yule branching process? I mean, it's a branching process. So this is like number of alleles. This is one, the orange locus here or the blue locus here. And here I follow all the allele copies in the population forward in time, here from the bottom to the top, where I only include individuals or individual alleles at any point of time that do leave offspring also at the time of sampling, so very late here, right? So all these lines here say do have further offspring. So there are no deaths in this Yule branching process, but it's a so-called pure birth process. And this is just to be efficient, right? Say, of course, in the end, we only need these individuals that we do see at the time of sampling. It's a bit like, say, a coalescent process, but done forward in time and for the whole population, right? Good. So we assume that we do have small allele frequencies, and therefore these interactions can be ignored. As I said, we only track the copies of alleles that are destined for establishment, and therefore can still be observed at the time of sampling. And this is given by some establishment probability, P establishment. That does depend on parameters. Here, sigma stands in for selection. Of course, strength of selection doesn't matter. These are the locus effects here. This also does matter, and also time does matter, because as the trait mean progresses from its initial point towards the new optimum, also the selection strength will change, right? So selection is not constant, depending on when maybe a new mutation arises and enters the game, right? So it is something that also depends on time. Okay, so we have two processes in this Yule branching process. New lines are created by mutation. So this is proportional to the population-wide mutation rate theta I, which can be different for each locus. And say we only include a line if it's also then establishes. So this needs to be multiplied by the establishment probability. So this is the rate at which new lines occur. And then there's a split rate. So, of course, lines that are already there can have multiple offspring. And this is also something that is proportional just to the establishment probability. And this is a rate. So this is something that occurs per locus, and this is something that occurs per line as we go forward. And then we count and account of the copies of mutant alleles at all these loci. So that's a time inhomogeneous Ewell branching process with immigration. So immigration, that is the mathematical term for it, right? For course, right? Say what immigration is done by this mutation process. This generates new lineages here out of nothing. And now question is, right, say for the stochastic part of our theory, right, is there a limit that is reached here in the stochastic part, say while allele frequencies are still low in this establishment phase, before the interactions become relevant? So this is a mathematical question. So that says, right, we have here, there's only two loci, but imagine these are many loci, and we have like a statistics of number of lineages at all these loci, right? And there should be something like a joint distribution that counts the number of lineages at all these loci at some stopping condition. And we will do this step by step because we need to do this step by step. And at first, I will assume that we simplify our model considerably and assume that all loci have equal effects. Right? This is indeed an assumption that makes our theory a lot easier, and so I start here. So what does this mean? If all loci have an equal effect, right? So this means that this establishment probability that I talked about will no longer depend on the locus, right? It will be the same no matter where a new mutation appears at which locus, wherever, right? Remember that we ignore all interactions here, right? So also, linkage is not an issue here. Anyway, our theory will assume linkage equilibrium at all times, right? Good. So, new lines by mutation appear. So at that rate, and there's a split rate that looks like that, right? And, but if this is true, we can just do a change of the time scale here of this process and then say, scale this establishment probability out of the whole process, right? Just say we're only interested in the relative rates of events of either mutation or reproduction at all loci, right? But all these rates are just proportional to the same factor, P establishment. So by rescaling time, we can just ignore it. And this way, right, we do get two things out of it. We now all of a sudden do no longer have a time inhomogeneous branching process, because remember, this establishment probability was something that depended on time. But now we do have a time homogeneous branching process. And also we have uniform growth at all these loci, right? So this is just a growth rate that here is on that scale normalized to 1. And it's the same at all loci. And this makes our life very much easier mathematically. It doesn't mean that if we now form ratios of the ni to n1, so this is the number of lineages at the ith locus to like just another locus, and let's pick the first locus to n1, right? That these ratios here or distributions of these ratios become independent of the selection parameters, right? So see, also all the selection parameters here that are in hidden in the establishment probability no longer play a role after this time change. And we get a joint distribution of frequency ratios here that only depend on the mutation rates. Yeah, and this can be worked out. And say the result is a so-called inverted Dirichlet distribution that looks like this. And so it's still sort of kind of nice and easy, right? But the only thing here, say, to note maybe is that indeed this is something that depends only on the thetas here and there, but not on any selection parameters. Okay, but this is equal loci. Now let's do the harder part. What happens if we have unequal locus effects? But for simplicity now, assume first of all that we do not have any standing genetic variation, right? So we only start with new mutation as a first step. Now in this case, unequal locus effects definitely mean so that these establishment probabilities are different for different loci. However, approximately, like with Haldane's formula, so establishment is just proportional to the selection strength, and the selection strength at, all these different loci after the change of the optimum is just proportional to the locus effect sizes. And these locus effect sizes, these are these gammas here, right? So we have a ratio of establishment probabilities, right? Formerly this was just 1 with equal loci, of course, but now, so with different loci, so this is a ratio of the locus effect sizes here. Good. So we can do the same thing as before, this time change, by scaling out here, so this establishment probability. And in this case, we get something like that. So we get a theta I times gamma I for the new mutations, and we get a split rate of gamma I. Now, once more, and this is a good thing, right? So this is a time homogeneous Yule process, right? So we did get rid of this time inhomogeneity, which is technically the most problematic part of it. But now it has non-uniform growth, right? So the growth rates is, you see here, the split rates, this is sort of the growth at all these loci, right? This is now non-uniform, no longer 1 at all these loci. All right, so what can we do about that, right? So before we had just ratios of the number of lineages, right? So that at different loci, and we said that this is maybe a quantity that is good to consider and could have a distribution that converges and limit. Now we need to modify this a bit and say, all right, we introduce these sort of generalized ratios where we have lineages ni to an exponent, gamma 1 divided by gamma I divided by n1, and these generalized ratios, they will probably converge. And this is indeed the case. And we do get a joint distribution of these generalized ratios yi that now do depend, of course, not only on these theta I, but also on these gamma I. And they are given by a so-called generalized gamma ratio distribution. So I could write down the formula, but it's already 2 lines here, right? So it is like quite a bit more difficult than this inverted Dirichlet distribution that we had before. So therefore, I only write that. So the only information that I wanted to get across anyway is, so it's a distribution that depends on these theta I and on the ratios of the locus effect sizes. Good. So, but remember, right, so far, we have ignored standing genetic variation, and we did this like for a good reason. Because, so that this ratio of establishment probabilities is given by this gamma I divided by gamma j, right, and is independent of time, which is the important thing here, right? This only holds for t larger than 0, when t0 is the environmental change, right? For all the time before that, where the standing genetic variation builds up, this is simply not true. And that's because, establishment probabilities, or think of fixation probabilities, right? Only for positive selection are linear in the selection coefficient. And for deleterious selection before the environmental change, they are not linear, right? And so they're exponentially related to selection. And therefore, this simple relation just does not hold. Good. So, what can we do, right? Yeah, right. So there is one last trick that we do have available here, right? And this is, all right, we still do the same thing as before, but we start the whole process simply at the time of the environmental change, right? So before, we have always assumed that we start way back in time, right, with 0 copies at all these loci, and then just go forward in time. And now we say, all right, now we don't do this anymore. We start here at time 0 at the time of an environmental change. And then what we need to do is, of course, to account for all the guys that are already there. And to do this in an appropriate way, what we need to do is to enter them into the mutation part of it. This may seem a little bit surprising, but the reason simply is that now, right, new lineages can, of course, always be created by a new mutation, but also by the guys that were also already there in the standing genetic variation at the time of the environmental shift, right? So we include it here in the mutation part, and then say, all right, we have those. And then, of course, we have a split rate, say with every lineage as before. And so this indeed does the trick sort of to account for the standing genetic variation here. Remember also that we did not need to do this for the equal loci, right? Because there, no matter how the relation is to locus effects or whatever, like if all the establishment probabilities are the same, then this is always the case, both after and before the environmental change. So for equal locus model, we did not need to do this. There is the same theory with this inverted Dirichlet distribution, right? So that applies to both before the environmental change and after the environmental change. Okay. So, so we can still deal with it. How are these number of copies here chosen? Now, this depends, of course, on the model assumptions you want to have for prior of the environmental change. So is this adaptation from mutation selection drift balance? Then this should be picked from a distribution, this Ni of 0. Or is this maybe, you start with some fixed admixture proportion. You could also do that, right? And then, so this is maybe just a fixed number here. Good. As before, these generalized ratios here converge, and we do get a joint distribution, right? That now just depends, say, on these gamma I and sort of effective mutation rates. So where we have these these theta I now supplemented by the number of lineages that we initially had. Also, already this is something that tells you, right, when new mutation will be important and when it maybe won't be important, right? If this yeah, theta I is something that is typically larger than this ni of 0, then the whole process will be largely be driven by new mutation. And if this is typically much larger than these theta I, then say without large problems, you can even ignore new mutation and only do adaptation from standing genetic variation. Again, get these generalized gamma ratio distributions here with a more general parameter here, replacing only the theta I from before. Good. So that was the establishment phase, right? Remember, we still have also the second thing, right? Say to link this to the deterministic dynamics via the competition phase. So how is that done? All right, so we assume linkage equilibrium in weak selection, and then, says the selection equation for each locus can be written like that, and we also already had this in a few talks, I guess, right, where we do have, say here a part of directional selection here, and also a part of a disruptive selection that does play a role when we get very close to the new optimum in particular, right? So you see here, this is something that scales with the distance of the trait mean to the optimum. And while this is still large, this is a term that by far dominates over that one that is of the order here of the effect size squared, right? And this only will play a role if, this is very close to 0. So as others have done before, for this first phase, we entirely restrict ourselves to the so-called direction selection model. We ignore this second term. So we have that. And then, say when it's convenient to consider these things not in terms of allele frequencies themselves, but to form odds of allele frequencies and odds ratios. And in terms of these odds ratios, so then the dynamics can be fully written out like that. And so there's an integral, a little bit complicated still, but you see here is a term, gamma I minus gamma 1. And so if we have equal locus effects, right, so then this is just a 0 here, right? This simplifies. That means these odds ratios for equal locus effects just stay constant. And since these odds ratios here for small allele frequencies are just approximately the ratio of allele frequencies, and this is the same as the ratio of number of lineages at all these loci. How these guys are distributed. They are distributed by the inverted Dirichlet distribution that we already derived for the stochastic part, and that is just maintained throughout the deterministic phase. So that's very easy. And it's just a side remark, right? This does not only hold for this specific model here, but you could have say any other say form of time-dependent selection here, right? As long as you do have this simple form here, right? So that as long as say for this selection part here, right, for equal loci is the same for everybody, right? So as long as this factor is the same for at all loci, so exactly the same result with the inverted Dirichlet distribution holds. Okay, so we have the distribution on the odds ratios. So, but we are interested in the joint distribution of frequencies. So, but this just requires a transformation back from the odds ratios to allele frequencies. This can be done, and it gives something that looks ugly, right? As you see here. And it is now like a transformed inverted Dirichlet distribution, as you could call it, right? No need to look at the details here. Maybe just also that even after all these transformations, it depends here on the thetas and all the other parameters that we do have here. So have nothing to do, for example, with selection, right? So it only depends on mutation rates. So, but this was equal locus effects. Right. We can, of course, then or should also ask what happens with unequal locus effects. So things are as always a little bit more complicated, but so the idea anyway was that we use these modified ratios, as you remember, and we can also introduce these modified this on the level of the odds, so generalized odds ratios as before, with these locus effect sizes, and then we do see that indeed these in a deterministic theory remain constant, and therefore the same thing applies as before. Now, in the level of these generalized odds ratios, say they still conform to a generalized gamma ratio distribution, even when they grow large. Good. So again, we need to transform back from these generalized odds ratios to allele frequencies to get a joint distribution at our stopping condition. And here I now only write. So this can be done, right, but results in a very complex expression. And there, of course, so the question arises a bit there, say, what do we gain if we have a very, very complex expression for our end result here? And luckily, so although this is very, very complex, right, it is still a thing that is built from gamma distributions, right? In the end, we have some sort of gamma distributions as input, and then we, combine them in various ways and modify and transform them in various ways, right? But it still is derived from gamma distributions. And the advantage of that is that we can, very easily numerically evaluate the whole thing, right? So maybe, say it's not like very easy to gain insights just from looking at the formula, but so there is an easy way to numerically evaluate it, just because it's very easy to draw random numbers from a gamma distribution. So there are very efficient ways to do this. So we have good numerical handles to use this very complicated result. So, before we come to results, there is one more thing, as always, right? And this is high frequency standing genetic variation. Just two short remarks about that, right? Because our assumption so far was that all alleles start from a low frequency or start as new mutation, right? So, and usually, standing genetic variation with realistic parameters for these loci looks like that. You have these U-shaped distributions here. So, for various loci as depicted here, right? But, of course, how about frequent variants? There could be some that do not start very rare, but already, right, so in the standing genetic variation are relatively frequent. So this is allele frequency here on the x-axis, right? And here these guys would all be rare, right? But here it could be a little bit more frequent. Yeah, in this case, right, epistatic interactions in the static genetic variation do lead to slight deviations in our results, right? So this is all I can say, right? It's not too severe. We will see this in the results at one point or so. We just ignore that. On the other hand, right, of course, I mean, these alleles could be not rare, but really frequent. If we are here on this other side of the U, right? How about so these high frequency derived alleles at that point, right? Well, I mean, the obvious idea is that maybe we can include them by looking at the opposite allele, always the minor allele frequency, right, at all these loci, and indeed. This can be done, right? So we can do the theory here for minor allele frequencies, but need to do it separately, right, on both sides, here and there. And then there's one thing. If here these guys are not only segregating in the beginning, but also at the time of sampling, right? So these that are initially here are not yet fixed, are not yet, right, say, at frequency 1. But are still some of these are segregating. These are selected against after the environmental change, right? These are favored after the environmental change, and these are selected against. And this is why I call them the deleterious variants, right? But if they still hang around, right, then this needs to be compensated by additional progress here from this beneficial variant to reach our stopping condition, right, which is given by the mean rate hitting a threshold value. All right, so two minor complications, but with that, I'm now finally through my methods, and say we deserve to see some results. Maybe at that point, right, say, are there any questions concerning these methods, or say I could just go along with and now show some results. Here.
I was just wondering, are there any assumptions that you've made about that standing genetic variation for it to lead to only slight deviations? Are there specific restrictions?
Yeah. You mean for the frequent variants also, right?
For their effect sizes?
For effect sizes, no. I mean, no. It's mine. It's just the usual say additive trait model with any effect sizes and any mutation rates everywhere, right? And the usual scenario that we consider for standard genetic variation is mutation selection drift balance, right? So we do have just stabilizing selection prior to the thing, right? And then we say also in our simulations we equilibrate this for say long enough that we have mutation selection drift balance. So this is a usual assumption, and say there is no further assumption beyond that. And what it does, we will see in the results at one point, right? Say what this assumption that minor allele frequencies are rare in the standing genetic variation, what this assumption does and what kind of deviations occur, we will see in a minute.
I see. So you've assumed for that standing variation that minor allele frequencies are rare.
The theory, right? So the Yule process assumes that these minor allele frequencies are rare in the sense that it ignores interactions. It ignores interactions among the level of standing variation at different loci. Okay.
Okay, I'll wait.
So so there are, of course, interactions because of epistasis, right? Fitness epistasis due to stabilizing selection. and therefore this is not completely true, that these are independent, right?
Yes.
And and we will see at one point, so what kind of difference this makes, right? Good. Okay, some results, and let's first start to keep this somehow manageable with the equal loci, and then I will also do some slides about the unequal loci. So, for the first few slides, we assume equal locus effects, right? We start from mutation selection drift balance, as I just said, with an initial optimum, Z0, and then, we have this shift in the optimum, and then adaptation occurs from standing genetic variation and new mutations until the mean phenotype reaches a threshold value, as I've also said right here. And this is still smaller than this new optimum because we want to here have results about this rapid phase and not about this slow equilibration phase. Another thing that we do, right, I mean, there's always the question, the end result in a way is the joint distribution of allele frequencies across all these loci that contribute to adaptation, right? So this is a very, very high dimensional quantity. And there's always the question, how do we visualize this even, right? And one good way to visualize this that we found is this way. So we do marginal distributions for single loci to have something one-dimensional, but we do not do this simply for arbitrary loci, because then with equal locus, of course, all these marginal distributions for all these loci would just be the same, so this would be trivial, right? But we order these loci according to their contribution to the adaptive response. So there is one locus that, in this case, just has the largest shift of allele frequency. So this has the largest contribution to the adaptive response that we sometimes call the major locus. And then there is the second and third and so on locus, and we order these to the adaptive response. And this is then something, as we'll see, I mean, the next few slides, right, that already can show us the types of genetic architecture that we can observe. All right, let's first have an overview about that. The scenario that I consider here is something we have 10 loci, right? And we assume that this trait mean shifts from initial position of 0, where indeed now let's say all the locus, all the loci carry the one allele, right? To a value of 3.333. That means so there is 3 1/3 mutational steps, right, are needed, and then we stop these simulations and see where our allele frequencies are. And for example, something that can occur there, right? Say one figure, that can occur here is something like that, right? So, and what does this mean? So this is allele frequency and the x-axis, and this is just the density of these allele frequencies, right? So, and what we then sometimes see, right, is that we have a peak here at 1, consisting of 3 loci that are simply fixed, right? Then there are 6 loci here that peak here that, have not even started to contribute here to the adaptation, and then we have one locus here, right, that is on its way and is just at 1/3, right? So altogether we get 3 loci that have now, and 1 locus that is on its way, right? And has just reached this position. And these are simulations across very many replicates, right? And then this generates this distribution here. So ordered distributions, the largest loci with the contributed largest, this one that contributes a little bit, and these ones that do not contribute at all. So obviously this is a picture of single sweeps, right? So 3 loci have done a full sweep, 1 locus is on its way, and 6 further ones have not even started to do anything. However, for some other parameter values, we do get a picture like that, right? So we have still 3 loci that are here, 1 locus here, and others here, but it's no longer, say these peaks are no longer so sharp. We do get sweeps and some scatter, and we do get more loci that contribute to the whole thing. 3 here, a 4th one here, and certainly, like if you look at this guy here, so this distribution is also something that becomes visible. So we have kind of 5 loci that now contribute to it. Of course, we can change parameters further and get a picture like that, right? So where we now have like a pattern of, some still maybe completed sweeps, but usually here just partial sweeps. So from the largest contributions here on that side, to the smallest contributions here on that side, right? Say some loci that only contribute very little, and some loci that contribute a lot. And remember, right, this is for equal loci, right? So all these loci primarily have the same effect size and have the same mutation rate. And we just start our simulations prior to the environmental change. Equal, with equal initial conditions for all these loci, and then just simulate to get a mutation selection drift equilibrium before we start the whole process, right?
Can I ask a quick question?
Of course.
Sorry, can you explain what the y-axis is? I didn't understand this.
This is the density of these allele frequencies. I mean, if you're familiar with Wright's distribution, frequency distribution from population genetics, this is sort of the same thing. It's just for a single locus in Wright's distribution, right? So, I mean, so this is the allele frequency distribution here is on the x-axis. The allele frequency is on the x-axis, right? And the density at which you observe these allele frequencies across replicates is on the y-axis.
Okay, thank you.
Right? So, for example, right, so you may remember this for a single locus, right? Say mutation, selection, drift, balance. So this is, we had this before, right? This kind of shape, this U-shaped shape, something is something that comes out of Wright's distribution. So this is, say, in the limit of when, say, mutation rates are not too large, right? When mutation rates are really large, you don't get these peaks at the 2 boundaries, but the whole distribution is then more concentrated in the middle, right? For large mutation rates, but for small mutation rates, this is the typical shape of it, right? And so this is the same, say, way to visualize this as with Wright's distribution. That, I mean, for example, what does this mean, right? So it means here, take this red distribution. So this is a major locus, right? So this is the locus that contributed the most to the allele frequency changes here. And we want to record how much it contributes across replicates. So this means here there are few replicates where it just contributes 0.8. There are more replicates where it contributes 0.9, right? And there are even more replicates where it contributes 1 or almost 1, where it has fixed, right? So it really peaks here. And same for the others, right? Say, this is, for example, this blue thing is the 3rd largest locus, right? And this means here we have, say, some replicates where it only contributes as little as 0.4, right? But here, say, usually it will contribute around 0.7 or something like that, right? So in most replicates. So this is, say, how these distributions should be understood. So this is, say, a typical pattern of partial sweeps at many loci. But now, of course, we can go even further and say, sometimes also this patterns looks like this, right? That we now have, say some consecutive, curves here of one locus that follows the other here, and all these contributions of different loci become more and more similar, and even can become something like that, where now, say, we do not have no fixations at all. There are no completed sweeps at all, right? But really now we get into a phase where we have small shifts here. All right, and we can, of course, ask what makes the difference. And I mean, obviously, since I've already stressed this so much, right, you could have guessed that it's not selection strength or anything like this, but it's only mutation rates, right? And it is, so this one parameter that we call the background mutation rate, that is L minus 1 is the number of loci, in this case would be 10, L equals 10, right? Times the per locus mutation rate that here is assumed to be the same for all these loci. All right, why L minus 1? Okay, this is background mutation rate because it measures for each locus the competition that it receives from alternative redundant adaptive alleles in the genetic background, right? I mean, if there's only like a single locus that can do the trick at all, right, then it must reach fix in the end, right? So there is no way around it, right? No matter what the mutation rate is on that locus, it may be small or large, it must do the thing in the end, right? But if this, our one focal locus is not the only one that is there, but there are other loci that could do the same thing, and solve the same task for us, right? So then, say this matters for our focal locus because it now gets competition from these other loci. And this is what changes the type of the adaptive architecture, as we call it, right? So you see it here, right, from this theta background from very low values, right, then to this very interesting value of where we have exactly theta background equals 1. This is sort of the archetypical oligogenic case, as we call it, right? And then here on the other side, we do get these smaller shifts and this behavior that is typical here of highly polygenic adaptation. Now, of course, right here, we only have 10 loci here. Therefore, all these loci need to do some allele frequency change to accomplish the task in the end. Imagine if we don't have only 10, but if we have 100 or 1,000, right? What then happens is that all these contribute only very, very, very little, right? So everybody only does a very, very tiny shift, right? Good. Okay. So that was an overview. Now let's do like a little bit more here to show you that it's really mostly the mutation rate here that matters. We consider here an additive trait, equal loci, and say this is a slide to check the dependence on the number of loci that underlie the trait and the selection strength, right? So we have here this one case with 10 loci as before. We have here 100 loci here, right? We will consider weak selection and strong selection for both of them. And now we put the initial trait optimum in the middle of the phenotypic range. We start from mutation selection drift balance. We then shift the new optimum by 3 mutational steps, and we observe the shift of the trait mean after, we observe the allele frequencies at all loci after a shift of the trait mean by a single mutational step. So let's do this step by step. All right, so let's first do it for a small background mutation rate. What you see basically here is 4 times the same figure, sort of, right? I mean, so here, these solid lines are our theory lines, and these dots are simulations, right? And it is, there's almost no visible difference, whether this is now 10 loci or whether it is 100 loci, whether it's weak selection or whether it's strong selection. Right, we always get, in this case here, one major locus that often fixes, right, but carries the main weight of it. I mean, remember now this is adaptation only over a single step. If this one fixes, then this one does the job alone. There's a second one and a third one that is also visible and very little, of further say here, right? So what that shows is that it's not the number of loci that matters, right? You could have 1,000 loci or 10,000 or whatever, right? If the total mutational input, right, is not larger than that, right, we always get the same pattern. Good, let's go on with that and now get to theta background equals 1. So what we see here is still this pattern is largely independent of the number of loci and also independent of strong or weak selection. We do now see small changes here and there. For example, here for this 10 loci, consider this and this, right? So there are small changes that mostly come up here on the right-hand side where you still see some alleles hanging around, and these are some of these what I call deleterious variation from the standing genetic variation that have not completely vanished, so that are still hanging around at the time of fixation, right? And for strong selection, this is not the case because there is much less standing genetic variation in this case, right? The initial standing genetic variation actually, maybe let me, this is a bit larger, right? The initial standing genetic variation is actually these open boxes here. So this is, there's too much information in this figures, obviously, right? So these open boxes is the initial variation, and the closed symbols, these are the final allele frequencies that are approximated then here by our theory here and there. And you see, like for weak selection, there's more of this deleterious variation, but still this whole genetic architecture is still very, very similar here and there. And this is the same thing here for 100 loci, right? Also there, right? So we have this thing of some deleterious alleles that still hang around. One other thing that these dashed lines, maybe quick comment, right? So since most of these task is just done by the first 3 loci here, right? 1, 2, 3, right? We can also say and try, okay, why don't we just only use a 3 locus model and approximate it with only 3 loci and with appropriately chosen mutation parameters such that we match this theta background thing. And we see that even the 3 locus model here does a very good job in explaining, so the most important aspects here of this figure. Good. Let's go back to my pointer and now go to like higher mutation rates. Let's see, maybe again, we need this a little larger. yeah. And here for high mutation rates, we now do see very much stronger differences between strong selection and weak selection. And this is absolutely the case because of all these deleterious variants that still hang around here at the time of sampling with weak selection, but do not play a large role with strong selection. Also, we do see now here, this is what I wanted to say, right? So that we do now have, if you look closely, a little bit of a mismatch of our simulations and of our theory lines here, in the way that so these simulation data are more spread out, these distributions, and these theory lines predict that all they are closer together, right? Simulations here, for example, dark green, or this pinkish thing here, right? They are more to the sides than our theory lines. And the reason simply is that now we do start with, say, standing genetic variation that is affected also by negative epistasis, and therefore this spreads out the whole distribution a bit more, right? So this is what I said before, right? Ignoring epistatic effects in the standing genetic variation. This is what, the kind of, say, differences that we do see here. Okay, so, I mean, I should show, of course, also that our theory does a good job to describe this across, a very wide range of parameter space. All right, so far we had like only one single adaptation step here. We can do this also over, like, say, more steps and get more figures. But I think I will just skip this for now. Just means our theory also works for larger adaptation distances here. And maybe, like, as a final slide for this equal locus case, just say, right, so far we have assumed always, or in our theory we have assumed, and also in simulations we have assumed, unlinked loci. What happens if we include linkage, right? And we see this here, and these are just genetic architectures. Here, say, they're all for this interesting case of theta equals 1, right? For one step and for further steps, towards the new optimum here, mutational steps. And the main message certainly is, if you look here down these columns here and there and there and there, what you always see, right, is that very, 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 very little changes until we reach, in the end, really R equals 0. So loci that are completely, entirely linked, right? There, really visible changes appear. Very slight changes appear at R equals 0.001. What always matters, how strong is also selection, right? Selection and harmonic mean recombination rates would be equal around here, right? So this is this is the level where recombination is as strong as selection, as you can say. And also we have some small numbers here that you may see. So these are always, right, the additive genetic variants and the genic variants, right? So, and these tell you, for example, here, if you look here in this line, that there are already strong differences between these two things. So linkage certainly does play a role, right? But it just doesn't show up very strongly in these patterns here until we really have complete linkage. So, I mean, this is just to say we've ignored linkage, but it largely doesn't matter. All right. So in the last 10 minutes or so, let me still come to unequal loci. All right. So, One problem is, of course, our theory can do quite a lot with unequal loci, but still with unequal loci, we simply have a very, very vast parameter space, right? And it already took us a long time to explore this whole space for equal loci, but for unequal loci, it is still so much larger. So we need to restrict this somehow, right? And for today, and here I will only show two cases, right? Say one toy model, sort of, where we have one large and one small locus, right? And one also a little bit of a toy model, like where we have 5 large loci and 5 small loci. Good. So just to give you an idea in which direction results change in this case. With adaptation, either only from new mutations or also from the standing genetic variation, until the sum of allele frequencies reaches a threshold value, right? And this is, just note this, we have changed here the stopping condition a little bit. Or I mean, like for equal loci, whether we condition on the sum of allele frequencies or whether the condition on the trait mean, which is then just proportional to the sum of allele frequencies, is the same thing, right? But for different loci, it is more practical to condition on the sum of allele frequencies just to be able to compare results for different ratios of large and small effect sizes here, right? So because like if we don't do this, right? So of course, if we have many more only small effects, then we do need more alleles to reach the same goal here than we do it here. Then we sort of compare apples and oranges, and it's more of an apples to apples comparison if we introduce this stopping condition here. All right, and loci are either again ordered by allele frequency as we do it before, or also, so this is an alternative, of course, in this case, we can order them by effect size. And what kind of architectures do we observe? Okay, let's do first this very toy model, like of just 2 loci, just to start somewhere here, right? And this now is a case where where I order allele frequencies according to effect size, and in particular from these 2 loci, 2 effect sizes here, right? Same mutation rates at both loci, right? So this is adaptation, only new mutation in this case, and we observe it when the sum of the allele frequencies is just 1, right? And what's shown here is the allele frequency of the locus with the smaller effect size. And this is enough because, I mean, these sum up to 1 anyway, so the larger effect size is just a mirror image. You can imagine here to have a mirror image for the larger locus, right? But we've not included it to keep the figure a bit less, a bit easier, right? So only thing to show here that, I mean, so this is equal effect sizes, and here, so these differences become larger and larger. And what happens, of course, is that this minor, smaller locus here contributes less and less, and it's more, almost everything here, like say for a ratio of 3 that is contributed already by the larger locus here. So this is absolutely the thing that you expect, right? What happens, and you see here again simulations in our theory lines is of course also to show that we have a perfect match also in this case. Okay, so that's a toy model. Now another toy model, sort of, I mean, but now with 10 loci, and we assume we have 5 with a large effect and 5 with a small effect, right? And again, theta background rate of 1, that is the most interesting case for oligogenic adaptation. And say the optimum really, straight optimum changes just from one side of the phenotypic range to the other side, also to keep it simple. And first of all, we only do new mutation. All right. And now what we do now here is to change so the difference between these two groups of loci, right? So here everybody is the same. So this is the marginal distribution now at all these single locus, and it's all the same, of course, the marginal distribution, because this is not ordered according to effect sizes, right? But then here, of course, you now see differences coming up, right? So for the smaller locus and the larger locus here, so these are the larger effect size loci here that contribute more, and the smaller effect size locus less. And here the differences become larger. And here, of course, these differences is extreme. So the smaller loci only have effect size of 1/100th of the larger locus. And then you see almost everything, or everything really is done here by, so these larger loci, the others do not contribute at all. Note that this is only new mutation here, right? And also note that, this kind of distribution, right, gives only a very, superficial idea of a genetic architecture. So it's maybe a good idea again to switch to ordered effect sizes here. And then this is how it looks like. Again, our theory lines together with simulation dots here. And what we see is that, so this was equal loci, all the theory that we had before, that this remains remarkably stable for quite a long time here, and qualitatively even here, right? Until then, if changes are really, really large, then really something like happens. But these genetic architectures that we do see here are not too strongly affected by differences in these locus effect sizes. Good. Let's look at this now, right? So this is, again, this additive trait with unequal locus effects. Or in this case, of course, here in this line, it is equal locus effects. And this is the figures that I've shown you before, right? So this is this 10 locus model that we've seen before for the equal effect sizes. And now what we'll look at, what happens if we now make this locus effect size unequal. First, so one group, 5 large loci and 5 small loci with half the effect, or here 5 loci with 1/100th of the effect. Okay, and what you see is that, right? So that for small theta background, very, very little changes, right? So the whole architecture stays absolutely the same, right? Then on the other hand, right here, say for very high mutation rates, say it definitely does matter, right? So you see, for example, here, so these are the small loci that lag behind the large loci, or here they lag behind the large loci by quite a bit, right? And this is the interesting case of this oligogenic thing. So something in between here happens. And we'll now take a closer look at that to see whether we can maybe explain that. All right. So this is so our case for oligogenic adaptation here with the same and with different locus effect sizes. All right, so what you see already here a bit is that if you look here, and especially here, things become a bit more spiky, right? So these distributions here, if we have large differences in the locus effect sizes. And this is intuitively, of course, because the job needs to be done by fewer loci, the ones with a larger mutation, the ones with larger effect sizes. The others don't contribute too much, right? So this is a bit the same as if we do not have the same amount of adaptive material as if we have a lower background mutation rate. So we can indeed try and do this, right? And now say, okay, instead of having always the same mutation rates as the loci, but different effect sizes, how about if we have always the same effect sizes at all the loci, but change the mutation rate? Okay? We have a smaller mutation rate here at 5 loci, or here, right? And here, of course, I mean, this is the same figure, just there's like different replicates, right? But here, we really do different things in our simulations here and there. And you see that these results come out remarkably consistent here and there, right? So whether we change the effect size or whether we change the, say, mutation input, at least in this oligogenic region here, say, comes out to relatively similar patterns of the genetic architecture. There are some reasons behind it. One can speculate, right? Of course, like establishment probabilities in the end, say, depend on the number of mutations that start to run and the numbers that are picked up. So this is a product of theta times T establishment. So it is in the end a product of theta times something that is proportional to the locus effect size that matters. This may be behind it. Now, if this is the case, of course, then one could think that, say, maybe we can compensate for that by increasing just the mutation rates at these small loci, right? But what we also could do is not increase the mutation rates, but add standing genetic variation. Because, I mean, so far we have not done this. But of course, standing genetic variation is the thing that favors small loci because they are less selected against. So, and let's just do this, right? So now we have all these things with standing genetic variation, and we see it here. For equal locus effects, we had this. I mean, it just doesn't matter. It just gives completely the same result. But then here, like for unequal locus effects, we get this and this. And you see indeed that this reverses these differences that we see here partially back to our original situation. So if we include standing genetic variation, then differences in the locus effect sizes matter sort of even less than they matter here, right? Because the disadvantage of the small loci is compensated in part by the standing genetic variation. All right, it's time to sum up maybe, right? So what did we have here? So we have an analytical approximation for the joint distribution of mutant frequencies, for an additive trait with arbitrary locus effects and mutation rates. What I've not shown, or this can be extended to diploids, and also to different adaptive scenarios. For example, importantly, we have now, like, say, also adaptation to a sudden shift in the optimum. We can also do a moving optimum. And interestingly, this results in exactly the same genetic architectures. And the whole thing is relatively insensitive to linkage. We do find that the architecture type mostly really depends on a single parameter that we call the background mutation rate, and is relatively independent of selection parameters. And this even holds for unequal locus effect sizes to a degree, right? Of course, a lot needs to be done. And the first thing that definitely needs to be done is that we still need to explore the full parameter space for these unequal loci. These only have been the first few glimpses, right? Yeah. At my current speed, this will require another full year of work, I guess. But at some point, there will be a paper out. And then there's more things to be done. Of course, so we only had the rapid phase of directional adaptation. There is this equilibration phase that follows, right? An easy prediction for that would be, whoever gets beyond allele frequency 0.5, right, in the rapid phase will then fully fix eventually in the equilibration phase, and the others will move back, right? But yeah, so we can check this prediction, of course. But yeah, so the real difficult thing is the last line here. So realistic models of pleiotropy, population structure, and local adaptation. Yes, and all these things are important, right? The problem is that these are very, very, very parameter-rich models, and we are already struggling, like with the current model, to fully understand everything, right? So that, we'll slow down us further, but we'll certainly approach also these problems step by step. Good. Okay, but so far, what we do have 3 scenarios of polygenic adaptation, right? It is like, so this sweep scenario, if a theta background is very small, then in an intermediate range, we have this heterogeneous polygenic adaptation, or also oligogenic adaptation, and we have small shifts at many loci for a large theta background. And if we now focus on this oligogenic adaptation, so it's characterized by partial sweeps in this parameter region. It's predicted to be heterogeneous among loci and also among replicates. And if we now look at empirical evidence for that, there's of course a lot of evidence for partial sweeps in data, meaning these are larger changes than just subtle shifts, right? Completed sweeps are even rare in natural populations. We have this plateauing effect of allele trajectories in experimental evolution frequently. And across replicates, we've seen this also from Nela's talk, right? We frequently do have responses that are partially parallel. So it's not like random drift, right? So selection is definitely the main driver of it, but it's also strongly heterogeneous among these replicates. Sometimes some loci respond, sometimes others respond to the same final state on the phenotypic level, right? So this is important, right? And this is what's shown by these data from experimental evolution, and this would be something that is fully consistent with this scenario of oligogenic adaptation. And with this, I'm here at my thanks, and they go to Ilse Höllinger and Ben Wölfe, of course, on whose theses this work here is based, and funding, and to you for your attention. Thank you.
So Joachim, how would it look like if you do not start with 0, but maybe say 100 or 200 loci being needed before you have the shift in trait optimum? And would this have an effect when you have then a more, how would you predict this would look like, particularly in the case of linkage?
You start with, we anyway start with, genetic variation at maybe even a large number of loci. I've shown here figures from 100 loci, right? You mean, even more than 100 loci, or what is it? So if you start with standing variation at 100 loci, you do have lots and lots of copies at lots of loci to start out with, right? At time 0, at the environmental shift, right? So this is already included. The thing is that, we do start with, we usually do start with mutation selection drift balance. So in replicates, it's always like a different combination of alleles across these many loci in our starting configuration, right? So these are different draws from the starting configuration. It would look different, if we do this as you do it, right, from a unique admixed ancestral population at generation 0, right? Because then you do start with the same allele frequency across all replicates at all these loci, right? So this this does change the result, but it can, it can still be covered by the theory. But so the results then are changed because this very important stochastic input that is in this mutation selection drift phase, right? So then is not there. You start with something that is much more, much less stochastic if you start with, admixture or with, like in your experiments, with a fixed frequency of, from two founder populations. Concerning linkage, what we see, right, is that, I can imagine that then linkage may be more important, right? Because you have very, very strong linkage disequilibrium to start with. If you don't start from mutation selection drift balance, but if you do start with admixture, then you do have, say, much stronger even linkage disequilibrium in your starting configuration, right? And then this should matter more. So this should be explored.
Thank you. Thank you again, Joachim.
Okay, thank you, right?